The universe is filled with vast clouds of gas and dust, stretching across the cosmos in magnificent displays. These clouds, known as nebulae, are not just beautiful to look at, they are the cradles of new stars. Nebulae are the birthplaces of stars, where the magic of star formation begins. These cosmic clouds are mostly composed of hydrogen and helium, the most abundant elements in the universe, providing the essential building blocks for star formation. Gravity plays a crucial role in star formation, acting as the invisible hand that shapes the destiny of these clouds. Within these nebulae, regions of slightly higher density can begin to collapse under their own gravity, initiating the process of star birth. As the cloud collapses, it fragments into smaller clumps, each a potential future star. Each clump continues to collapse, pulling in more gas and dust from its surroundings, growing in mass and density. This process is driven by the relentless pull of gravity, which ensures that the clumps continue to gather material. The collapse of these clumps releases gravitational potential energy, which is a key part of the star formation process. This energy is converted into heat, causing the temperature at the center of the clump to rise dramatically, reaching millions of degrees. Over millions of years, the core of the collapsing clump becomes incredibly hot and dense, setting the stage for nuclear fusion. This hot, dense core is known as a protostar, the precursor to a star, marking the beginning of a star's life cycle. A protostar is a young stellar object, still in its early stages of formation. It is a hot, dense ball of gas that is still contracting under its own gravity. Protostars are not yet true stars because they do not generate energy through nuclear fusion. They emit light, but it's not from fusion. As a protostar continues to accrete material from its surrounding cloud, its core temperature and pressure continue to rise. The protostar's intense gravity pulls in more and more material. This process can last for millions of years. Eventually, the core of the protostar reaches a critical temperature of about 10 million degrees Celsius. At this temperature, nuclear fusion begins. Hydrogen atoms, the most abundant element in the universe, are fused together to form helium. This process releases an enormous amount of energy, marking the birth of a star. Nuclear fusion is the process that powers stars, providing the immense energy that makes them shine so brightly in the night sky. It is the process of combining lighter atomic nuclei into heavier ones, releasing a tremendous amount of energy in the process. This energy is what fuels the light and heat emitted by stars. In the core of stars, the intense pressure and temperature create the ideal conditions for nuclear fusion to occur. These extreme conditions are necessary to overcome the repulsive forces between atomic nuclei. The most common type of fusion in stars is hydrogen fusion, where hydrogen atoms are fused to form helium. This process is also known as the proton-proton chain reaction. In this process, 4 hydrogen nuclei, or protons, are fused together to form one helium nucleus. This fusion process releases a significant amount of energy in the form of light and heat. The mass of the helium nucleus is slightly less than the combined mass of the 4 hydrogen nuclei. This small difference in mass is crucial for the energy release. This difference in mass is converted into energy, as described by Einstein's famous equation E equals mc squared. This equation shows that mass can be converted into energy, explaining the tremendous energy output from fusion. The energy released from nuclear fusion in the core of a star creates an outward pressure. This pressure is essential for maintaining the star's structure. This outward pressure counteracts the inward pull of gravity, preventing the star from collapsing under its own weight. The balance between these forces is what keeps the star stable. This delicate balance between gravity and pressure is what allows stars to shine for billions of years. It is this equilibrium that sustains the star's life cycle, enabling it to continue burning brightly in the cosmos. Once a star achieves hydrostatic equilibrium, a state of balance between gravity and outward pressure from nuclear fusion, it enters a long, stable period called the main sequence. This is the longest stage in a star's life, and it is during this phase that stars emit the vast majority of their energy. The main sequence is not a single point in a star's life but rather a stage that encompasses a range of stellar properties. Stars on the main sequence can vary significantly in terms of their mass, temperature, luminosity, and lifespan. The mass of a star is the most crucial factor determining its evolutionary path. More massive stars have stronger gravitational forces, leading to higher core temperatures and pressures. This results in a faster rate of nuclear fusion. making massive stars hotter, brighter, and shorter-lived than their lower-mass counterparts. Section 5. Stellar evolution, the red giant phase. As a star ages, it gradually exhausts the hydrogen fuel in its core. This process takes billions of years for sun-like stars. Eventually, the core runs out of hydrogen to fuse. Without the outward pressure from fusion, the core contracts and heats up. This heating ignites hydrogen fusion in a shell surrounding the core. The outer layers of the star expand dramatically, and the star becomes a red giant. Red giants are much larger and cooler than their main sequence counterparts, giving them a reddish appearance. During the red giant phase, the star's core continues to contract and heat up. In stars like our Sun, this eventually leads to the fusion of helium into carbon and oxygen. This process releases even more energy, temporarily prolonging the star's life. Section 6. The fate of stars, white dwarfs, and planetary nebulae. The fate of a star after the red giant phase depends on its mass. Low-mass stars like our Sun eventually shed their outer layers into space. This creates a beautiful expanding shell of gas called a planetary nebula. At the center of the planetary nebula lies the star's exposed core, a dense, hot object called a white dwarf. White dwarfs are incredibly dense, packing the mass of the Sun into an object roughly the size of Earth. They are incredibly hot but no longer generate energy through fusion. Over billions of years, white dwarfs slowly cool down and fade away, eventually becoming black dwarfs. Black dwarfs are hypothetical objects, as the universe is not old enough for any white dwarfs to have cooled down completely. Section 7. Stellar cataclysms, supernovae, and neutron stars. Medium-mass stars, several times more massive than our Sun, experience a more dramatic end to their lives. As they exhaust their nuclear fuel, their cores collapse rapidly. This collapse triggers a catastrophic explosion called a supernova. Supernova are among the most energetic events in the universe, briefly outshining entire galaxies. The explosion ejects the star's outer layers into space, enriching the interstellar medium with heavy elements. At the heart of the supernova remnant lies an incredibly dense object called a neutron star. Neutron stars are composed almost entirely of neutrons, subatomic particles with no electrical charge. They are incredibly small, typically only a few miles across, but incredibly dense, packing more mass than the Sun into that tiny volume. Section 8. Cosmic abyss, black holes. The most massive stars, more than 8 times the mass of our Sun, meet the most extreme fate. When these stellar behemoths exhaust their nuclear fuel, their cores collapse under their own immense gravity. This collapse is unstoppable, and it creates a region of space-time from which nothing, not even light, can escape, a black hole. Black holes are characterized by their intense gravity, which warps the fabric of space-time around them. They have an event horizon, a boundary beyond which escape from the black hole's gravitational pull is impossible. Black holes are enigmatic objects, and their properties continue to fascinate and challenge our understanding of the universe. They play a crucial role in the evolution of galaxies, influencing the motion of stars and gas within them. Section 9. Stellar legacy, enriching the universe. Stars are not isolated objects but rather integral parts of the cosmic ecosystem. They are born in vast clouds of gas and dust, known as nebulae, where gravity pulls the material together to form new stars. These stellar nurseries are the cradles of star formation, where the delicate balance of forces gives birth to new light in the universe. Throughout their lives and even in their deaths, stars play a vital role in enriching the universe with heavy elements. As stars age, they undergo various stages of evolution, ultimately leading to dramatic events like supernova explosions. These cataclysmic events scatter the elements forged in the star's core across the cosmos. Nuclear fusion in stars creates elements heavier than hydrogen and helium, such as carbon, which is a fundamental building block of life. This process occurs in the intense heat and pressure of the star's core, where lighter elements fuse to form heavier ones, releasing vast amounts of energy, oxygen, and iron. These elements are crucial for the development of planets and the emergence of life. Iron, for instance, is a key component of planetary cores and is essential for the magnetic fields that protect life on planets like Earth. These elements are essential for the formation of planets, life, and everything we see around us. The dust and gas enriched by previous generations of stars coalesce to form new planetary systems, each with the potential to harbor life. When stars die, They return these heavy elements to the interstellar medium through supernova explosions and stellar winds. This recycling process ensures that the material is available for future star and planet formation, maintaining the cycle of cosmic enrichment. This enriched material then becomes the building blocks for new generations of stars and planetary systems, perpetuating the cycle of birth, death, and rebirth in the universe. Each new generation of stars inherits the legacy of those that came before, continuing the cosmic cycle of creation and destruction. This ongoing process shapes the evolution of galaxies and the large-scale structure of the universe, influencing everything from the formation of stars to the development of complex life forms. The universe we observe today is a testament to the life and death of countless stars that came before. Each star's journey contributes to the rich tapestry of the cosmos, weaving a story of creation, transformation, and renewal. The atoms in our bodies were once forged in the fiery hearts of stars, connecting us to the vast cosmic web of existence. This profound connection reminds us that we are part of a larger, ever-evolving universe, bound by the same forces that govern the stars.